please do not swear. No, that's just me, isn't it? Let's go back to that one. Where's my thing gone? That one. There we go. Right. Thank you very much. This is the first in a series of around various different statistical techniques, etc. And what we're going to have a look at originally is a bit of correlation analysis. So this is lunchtime learning with Simon and no crisps. So let's start off with a few little ground rules. There will be prizes for the best learner. So do put your answers into the chat or shout them out, whatever, and I will be keeping a very vigilant scorecard. So like I say, do need you to shout out answers because I haven't got access to the chat. So yeah, shout out answers where you can, or put them in the chat and I'll look back in a minute. There are wrong answers, so none of that. There are no wrong answers. Yeah, there are wrong answers, definitely. There will be some trick questions. Like I said, there is a quiz as we go along. Anybody not shouting out or putting answers in the chat will be picked on, so just fair warning on that score. There may be some lines to the ground rules, but you can work out which ones that is. The answer to the penultimate question is 12,402. You might want to keep a note of that. And trigger warning, in my PowerPoint, some of the graphs might not be absolutely super duper aligned, and I know that causes some people grief. So without further ado, what are we talking about? We're talking about correlation, which there are a number of various different things around things. There are various different definitions around what correlation is, but it's basically you've got two variables or two or more variables. You've got X and Y. Does a change in X correlate or change as Y changes? So very, very interesting correlation is ice cream sales and shark attacks. As ice cream sales go up, there is also a direct correlation that the number of shark attacks goes up. Very famous correlation, but does bring us on to this next sentence. So question one, here we go. Correlation is not
causation.
There we go. Look at who said that.
Leonie.
Oh, there we go. That's the very short answer. But let's go for the full version. So you get 5 points, but for 10 points, you would obviously come out with the full one. So correlation is not causation. Obviously, in my shark and ice cream example, the causation factor is probably the temperature, as when it gets hotter, people eat more ice cream, and they also eat sharks eat more people because they're out and about, because there's more people in the sea. So, like I say, correlation is not always a attributable to causation. However, it can be. So even though we say correlation is not causation, there is quite often a direct causation link, and there are ways of establishing that. So congratulations. So let's look at our analytical question that we are going to explore. So we have 4 hospitals. Hopefully everybody knows what a hospital is. All of them do a number of widgets, okay? And a percentage of those widgets get sprangled. Hopefully you're totally okay with all this terminology and I'm not talking about anything you don't understand. So what we want to know is there a correlation between the number of widgets and the percentage of widgets that get sprangled? Okay, so hopefully a really applicable real world example that we've all encountered many times. So basically, how do we determine if there's a correlation between X and Y? So let's look at some graphs. Hopefully you've all seen graphs before. So we have St Luke's Hospital, St Boba's Hospital, St Hans Hospital, and St Leia's Hospital. No points for guessing where I was inspired by. So we're going to have 3 questions, and if you could put your answers in the chat. And yeah, let me get the fabulous countdown music. We're going to have 30 seconds to answer those 3 questions. Ready, steady, go. Haven't seen any answers yet. Analyze that data. Come on, you can do this.
I'm writing the answer down for some reason.
Don't put it in the chat. I can't see it. Always shout it out. What is going on here? Oh, we're nearly there. Five seconds. So, oh, look at that. Aaron's showing off. Possibly. Are you making those words up? Anybody got an answer? Anybody know which one is the most correlated? Can tell from that? So yes, we will use a statistical test. We're not going to use chi-squared or chi-squared or any of those. Anybody else got a correlation guess?
I don't think you can tell.
Don't think you can tell? Okay. Two most correlated bobas. Yep, I think Chris has hit the nail on the head. It's a trick question. There's virtually no way you can tell. And lots of people going for bobas though. That's interesting. That's interesting. Okay, let's have a look then. So the other big question is question 4. Has anybody ever done a plot like that before? Or have you seen those type of plots before? I've seen those type of plots with another line on top on a different scale to supposedly show correlation. I've seen it. I've seen it in some of the reports we send out weekly, which is yeah. Anyway, moving on. Let's have a look and see if we can establish what the answer is then. So let's have a look at the graphs. So the correct answer is St. Layers, which has a perfect correlation. But obviously, we probably need to break that down a little bit and look at how, why, etc., etc., because it's totally not visible from that graph. So question 5, hopefully a very, very quick and easy yes or no. Are you thinking that dual axis graphs are perhaps not the best way to determine correlation? Yes or no?
Yeah.
So yes, yeah. So if you're thinking that, yes, you'd be correct. And if you're thinking, no, that's really good, sorry, you're wrong. And let's show you why. So let's have a look at St. Bobas. There we go. Many of you chose that one as the one with the most correlation. Where are we? So, some rhetorical questions now. Is there a better way of showing correlations? Can we calculate the strength of the correlation? Do correlations always go in one way? And the absolutely big one is there a simpler way to show correlations visually? One that is simple, and as I say, you probably feel so simple for not using it. So let's have a look at that same data, but on a scatter plot. And we can very, very clearly see there is a really good correlation between the number of widgets and the percentage of widgets sprangled. As we can see, as the number of widgets goes up, we can see there is a really, really straightforward correlation between those. So we can almost see, there we go, we've got a lovely, lovely straight line. So, but how can we quantify and actually statistically describe that relationship? That's what we want to get to. So what would be useful if we could somehow, we can see that there is a line, it's quite clear, but how can we actually draw and fit that line onto that graph? So let's start with the simplest line that we could possibly try to draw on there. So let's just start with our mean of widgets, which is just a very straight line, which is going to show our mean. We can see that is not a very good fit. What we want is a nice sort of diagonal line that's going to hit all of our data points. So we can see it's not a very great fit, but what we can determine is how much of a not very good fit it is. And we can do this by calculating the distances from our data points to our mean. So we've got a distance here, we've got a distance here, and we've got distances between all our data points to the mean. Does that make sense? Nothing too complicated there. And what we can do is, obviously some of these distances are positive and some of them are negative. Some of them are closer, some of them are further away. If we square those distances, a negative times a negative comes out as a positive, and it also gives some weighting to those that are further away to the line to those that are closer. So if it's really close, it will have a smaller number, but obviously if you're getting further away, it's a larger number. And what we can do is add up all of those distances and then take an average of them. And what we want to do is try to get to a point where if we adjust this line and make it slightly more here and then do another recalculation, what we want to get to is the line where we've got the lowest possible sum of those R squares. Does that make sense? So what we want to do is create a line that's going to be this way. The distances are going to be small, and when we square those distances and add them up and take the average, we will have the absolute smallest amount left over. So the distance from our line here are called our residuals. And what we can do is add up the squares of our residuals to come up with a line that has the lowest residual squares, or R2 for short. So, or R squared for short, R2, sorry, that's a Star Wars, so I'm getting muddled up again. So yeah, R squared for short. So the R squared, the overall number will tell us how far away our line is from our data. So let's fit a lovely line onto our data. We can do this by doing maths, which is really good. So we can get our fingers out and plug in our variables to a lovely formula, which will work that out. As I always say, stupid people do maths, clever people get computers to do maths for them. So, you know, let's not do the lovely formula. Let's just chuck it into the computer and it will give us this answer. So looking at our line here, those were our residuals, and then we're going to tilt it around. And what we come up with is a lovely line that pretty accurately describes our data. We have got a few points that are slightly off the line, and we've also got a few that are, you know, reasonably far away from the line, but hopefully you can see that's a pretty good fit. So that's what we end up with. And what that's called is a linear trend line. So anybody can give me a property of that line? As in, what shape is it? The clue's in the question. What shape is the line?
A straight line?
It's a straight line. Absolutely perfect. Who said that? I didn't see who. That was Aaron. Some points for Aaron. Well done, Aaron. So it's a straight line. So therefore, it might not always be the best possible fitting line, but it is the simplest one to understand and also obviously get across to you. So we can describe a line in any straight line on a graph by where it hits the y-axis, which is we call the intercept. And also we can describe the slope of the line, as in one increase of x, how much would be the increase in y? So let's say this was 0.00 here on our line, and then we can see very roughly that for every increase of 1 unit in x, we see an increase of y of about 1.5 and a bit, which is obviously a very technical way of understanding how that is. So we can describe the slope, and we can also see where this will hit the x-axis. And from that, you can describe a straight line on a graph. Obviously, this line does not, the scale on this doesn't go down to the fully expanded axis. So does everybody kind of understand what the intercept is? That's if we drew this line right back down to 0, where it would hit the the y-axis, and also the slope is for every increase of 1, what's the increase of 1x, what's the increase of y? Does that make sense? Hopefully that's not too tricksy. Do shout if you are stuck. So what we can also describe is the overall distance of our data from our fitted line, which is our sum of r squared. So looking at that, sorry, it wibbled around a bit there. So we can extend our plot. Oh, sorry, I did do this earlier. So yeah, we can extend the plot further. So this now does have going down to 0, and we've extended our line out. We can see that 22.3 here is our intercept where it comes through. And it says at no widgets, there would be 22.3% sprangled, which is this point here. Obviously, if these things are directly the same thing as we're talking about these widgets and what percentage of those get sprangled, real world might not be appropriate, and so obviously models do fall down with sort of real world examples. So like I say, sometimes there are common sense issues with modeling, but you just kind of need to understand that. We can also see that in every increase in x, there will be an increase in y, and we can calculate that. So we can see that for 0 widgets, there will be 22.3 sprangled, and for each additional widget, we would see an estimated 0.04% sprangled. So if we want to calculate a guess of how many were sprangled at 50, we would take 22.3 and then 50 times 0.04, and that would give us an estimate of where we think this point here is. Does that kind of make sense? Yeah. And we can also describe the overall distance of our data from our fitted line. So we've got our data here. It kind of hits most of the points, but as we know, and we can see, there are a couple of points here where it doesn't hit the line. So we calculate our residuals and square them and take the average of those. And that always comes out with a number between 0 and 1, which is nice and convenient. And what we want is a really nice high number. In this case, our R is 0.976, which basically says that 97.6% of our data fits on that line. So we've got these two little bits here which don't quite fit the line. If we had some outliers, which I'll show you later, we can see that that line would not be so good. Where are we? So let's go back to those lovely graphs. So can you see anything strange about St. Luke's and St. Govor's? Is the question. Specifically those two. Anybody? Again, super horrible trick question. Let's plot them on a thing. It is exactly the same data, just in a different order. And the scale is being altered on St. Luke's. So there we go, to prove it, exactly the same data. So again, doing these lovely sort of correlation type things with two scales, really dodgy practice, and very heartily not recommended to do that. If you want to show a correlation between two things, this is not the way to do it, because you can so easily just completely alter what you're showing by sort of visualization. So remember about that, especially later on we're going to talk about linear scale, linear lines on time series. So where are we? So let's have a look at these two. We've got St. Hans and we've got St. Leia's. Let's have a look at St. Hans. Anybody think that's correlated? Any yeses? Hands up for yes. Hands up for or I don't know what the other options are. What else can you do that apart from hands up? Hands up for yeses. Anybody? So again, really trick question. Let's have a look at that on a scatter plot. I hope we can see that there is next to no correlation there whatsoever. Even though, but your eye is really good, and your brain loves making patterns where there aren't any. So we can see that that kind of goes up and then it kind of goes down, and oh look, that's definitely there, that's definitely correlated there. And then, oh, it's kind of gone down and that's gone down. So your brain will make up these correlations where they really, really do not exist. And it will ignore these absolute misses where it's like, you know, that's gone up, that one's nowhere near, that's well below. So again, just using that kind of methodology to try to find a correlation is really great practice. Your super simple scatter plot is your friend. So we can certainly see from this data that we've got it all over the place. So let's put a linear trend on there. We do still have a trend, okay? And like I say, definitely in quotation marks, we do have a trend line. You will always get a trend line of some description. Unless your data is perfectly symmetrical, it's very unlikely to come out with a completely flat line. So there will always be a trend of some description. However, I hope you can agree that that is not a trend that we should be talking about or is in any way significant. So what we want to do is look at our stats. So we have intercept of 25 and we have a slope of 0.13. So we've got this absolutely tiny little slope. That's not necessarily a bad thing. You can have a really good correlation with a really poor slope. You can have a really bad correlation with a really deep slope. It just means your data is still all over the place. More importantly is when we look at our R values, so if we look at how close our values are actually to our plotted line, we've got an absolutely terrible R squared, which is 0.028, which basically means our plot here only fits 2.8% of our data. So even though we've got a trend line, it's absolutely rubbish and does not fit the data. Does that make sense? Please shout and scream if anybody is stuck. So moving on. We also have a really good statistic which helps us kind of understand that, which is called a p-value. Something that's used in research, in scientific papers, all over the shop. I'm sure you've heard, or hopefully you've heard of a p-value. And basically what that does is a test of statistical significance. And we're all analysts, so we should be all over statistical significance. I mean, that's absolutely what we should be doing. So like I say, what that does is looks at that observations. So yeah, so sometimes you will have, you know, we've got a few observations here which are relatively close to the line, and then some that are miles away. And this p-value will basically, like I say, tell you whether it is significant or not. There is a lovely, hideous bit of algebra in order to work that out. Again, we're not going to look at that. We'll save the maths for later. But basically, our p-value will tell us whether our data is purely random and we might just happen to get to this sort of line by chance, or actually whether it is likely that this is true. So what we want is to get a p-value of less than 0.05, in which case we can reject the null hypothesis. If our p-value is above that, then it basically shows that our data is too random and we cannot be statistically assured that our trend is significant. So let's have a look. In this example, our p-value is 0.64, which is way bigger than 0.05. So we can absolutely not reject the null hypothesis. Our null hypothesis is that the data is messy and makes no sense whatsoever, which hopefully you can see from that scatter plot that that's absolutely what is going on. So we can only conclude that the correlation here is not statistically significant. So absolutely super duper whooper important. We do still have a slope. So no matter what, let's say it's really, really, really unlikely that you are going to come up with a data set that will not have a slope in some shape or form. But this slope is not statistically significant, and we have very large residuals, which is our R squared. So remember that. It might come up in a quiz question later, who knows. So what have we learned? A flat line on our trend shows that there's no correlation. A line sloping up shows that there's a positive correlation, as in an increase in X, there is an increase in Y. So what is next? St. Leia's Hospital. If you remember right back, we had that. So let's have a look at the St. Leia's Hospital. Question 8. What is going on here? And hopefully you're going, Simon, that's rubbish. You've given us a really rubbish graph. There's no way I can tell what the correlation is from that. So let's have a look at it on a scatter plot. So now who can tell me what's going on?
You have a negative correlation.
Boom! Look at you. Bonus points there. We have a negative correlation. So we do have an absolutely perfect negative correlation, which again is ridiculously hard to see within this graph, but super duper easy to see within our scatter plot. So let's bring that over. And what do we see? We see a super straight line. Let's put our line on it, and it's absolutely perfectly correlated, as in every line is absolutely straight through on that intercept. So we have an intercept of 30 and we have a slope of minus 0.04. So basically every increase of widgets, we get a decrease of the percentage that gets sprangled. So it is a perfect correlation, but it's a perfect negative correlation. So as we said, as I just said, because I didn't know that. So what we have is an R squared of 1, which basically means it's perfectly correlated. There is no distance between our dots and our line, not a single slither of a piece of data. So we still have an R squared of 1, which means our data is perfectly correlated. So we can see correlations can be positive or they can be negative. So we just need one more little bit of statistics to be able to describe whether it is a positive or a negative correlation, which we use. My mate Pearson came up with the lovely Pearson's correlation coefficient, which has got a really, really horrible and scary looking equation, which we are going to completely ignore. Basically, we can feed the data into Pearson's correlation coefficient, and it will give us a number from -1 to +1, going through 0. So in essence, -1 would be a just centers around the mean perfectly, and it's perfectly symmetrical. And then +1, which means there would be a perfect positive correlation. Just remember, this has got nothing to do with the slope angle. So you can have a really shallow perfect correlation, or you can have a really steep perfect correlation. It just means that that increase of X to the relationship to the increase of Y is absolutely spot on. So for every increase of widget, you get an extra 1 widget sprangled, or you could have 1 extra widget and it will give you 100, but each time it's absolutely perfect one way or the other, or a minus. So like I say, it's got nothing to do with the actual slope angle, so don't necessarily think the slope angle has anything to do with that area. That's a different bit. So a bit of a recap. We've got our intercept, which is where our magic line meets the x-axis. We've got our coefficient, which is for the increase of 1x, how much does y change, whether that's positively or negatively. We've got our R squared, which tells you how good a fit our trend line is, a value between 0 and 1, and we can convert that into a nice easy percentage. And we've got my mate Pearson and his correlation coefficient, which will tell you whether it's a positive correlation or a negative correlation. And then finally, we've got our p-value, which will tell us whether our correlation is statistically significant, which does take into account your R squared and a few other bits within that calculation. But again, I'll let you guys go and explore the maths about how all those are done. So let's have a look at all our lovely hospitals again and have a quick look at our stats, and hopefully we can have a look at them and understand them. So St Luke's and St Boba's, exactly the same because I really cheated and put the same data in twice. We've got our intercept, we've got our coefficient, we've got our R squared of 0.97 because we've got pretty good fit, but we have got some that are not on the line. We've got a p-value of less than 0.1. It's absolutely, so we want a smaller p-value as possible. We want big R's and small p's. I'm sure there will be a fabulous way of trying to remember that, but I can't. And then we've got our Pearson's coefficient, which tells us whether it's positive or not. Because we have got a few that are not on the line, it's not absolutely perfectly. So this guy here has kind of messed it up, but we are pretty close to 1, so we can be pretty assured that that is a pretty positive correlation of what's going on there. We've got St Hans here, where we've got our intercept. We've got a really what's going on there? That's wrong, isn't it? The R squared should be massive. I've obviously put the wrong number in there. We should have a really massive R squared, not small. Oh no, sorry, other way around. No, we want R squared to be small as well, don't we? Sorry. Yeah, we want small R's and small P's. Getting it muddled up now. So yes, we've got a really small R, which means that it does not fit our data very well. We've got a large p-value, which means it's all over the place, and we can't be assured that it's statistically significant. And hopefully you can see from the data that it's not hitting all those data points. And then we've finally got St Layers, where we've got a perfect R squared. In that our data is perfectly aligned to our line. We've got a very good p-value in that we're really assured, and we've got a perfect -1 on our Pearson coefficient because all the points hit there perfectly, and it's a perfect negative correlation. So near the end of the session quiz, question 9: is putting two axes on a graph a good way of showing correlation? Hopefully I've convinced you now that no, that's a really bad thing to do. Question 10, same as question 1, I think it is correlation causation? Absolutely not. Things can be correlated. Quite often can be causation. That's not to say that if you've got a correlation, it doesn't mean that there is a causation. It's just further investigation is required to actually establish that. So without a doubt, you know, if I looked at number of pies that I eat in a week and compared it to my weight, I'm pretty sure there's a causation factor there. So, you know, without a doubt, you can have direct causation. So don't necessarily, I know it's drummed into people that correlation isn't causation. Sometimes it is, and don't eat too many pies. So what shape is a linear trend? Again, I think we've already answered this question many times, and it's very important just to get that stuck in your head. It is a straight line, and there are some times when that's not a good thing. And does a good slope mean a good fit? So if you've got a very nice sort of 45-degree angle, does that mean that your slope is a good fit? No, it doesn't. So we always take into account your residuals and your p-value. You can get a really good slope on some really crazy data. A couple of outliers can throw your slope like goodness knows what. It's thoroughly recommended that you, or I might put some stuff into, even just playing with an Excel with a linear trend and just putting some outliers in and just seeing what a massive effect it has on your slope so quickly. Question 13. Is a linear model a good way of predicting a time series? So again, something I've seen on a fair number of reports, something I put my hands up to, that in the past I've pressed the lovely linear trend button on Excel to show, well, look, this is the numbers of referrals we've had, and here it will be in the future. The answer is an emphatic no. That pure trend line with no thought of your R squared or your p value is just literally a line, and you could just be talking complete nonsense. So don't do that. I think I'll go into that in a minute. So what we have taught you, or I have taught you by the back door, is something called linear regression, which sounds far more fancy pants than correlation analysis. But it is an absolutely fantastic and amazing thing. So question 14, if we had 120 widgets, what would we predict our percentage strangled to be? Anybody?
About 27.25.
27.25. Perfect. That's literally what you've just done in your head there, or by squinting at the screen, is the absolutely basis of unsupervised machine learning, which is a whole world of amazing stuff that is out there. But basically, just being able to create a prediction based on sparse data and coming up with a reasonable prediction of what you think it will be is a phenomenal thing. And we can go into that probably in a few more lessons in the future's time. But that, like I said, that is absolutely the basis of a lot of machine learning models. Back to question 13. So, is linear regression good for predicting trend on a time series? So let's pretend these are our months going across. We've got a trend. Would we feel confident to say, oh, look, our trend is going up? No, basically, because our linear trend, our linear regression will basically just plot a line. It may or may not be significant. It basically just converts the months into a very simple unweighted number. So it's really not very helpful. You need to have a look at your residuals. So even to say, oh, look, our trend is going up. Our data is all over the place. There is no confidence there whatsoever that that trend is significant. And like I say, it only gives a straight line, and without supporting statistics, it is literally just a straight line you've drawn in pen on top of your graph. I can do that under this, can't I? Can I do that? I can go. You may as well just go, oh, it's going to go that way, which is, you know, absolutely of no use whatsoever. I forgot I could do that. So, on that, there are far better ways of doing time series analysis, and happy to do a topic on that for another day. There are fantastic models which look at which weight your time series, take into account seasonality, these decompose all your data by trend and, let's say, seasonality and noise. There are proper ways of predicting and analyzing time series, which, like I say, we can do another day. But a linear trend is not your friend for that. So next steps. What if we want to understand the linear relationships between widgets, percentage of widgets sprangled, and the numbers of plumber squint? So instead of just having two factors, what happens if we have three? Obviously, we can just plot a nice 3D graph and create a 3D plane. The question is, what happens then if we want to convert the relationship between four variables? That's when it all gets really tricky, because I don't know about you, but my brain doesn't work in 4 dimensions at all. It hardly works in 3, to be fair, but 4 is just way out there. I don't think there's a monitor that could possibly even can do that. So absolutely impossible to plot. There are kind of ways around it. We can reduce the dimensions of our data by doing this funky thing called principal component analysis, but that's definitely a topic for another day. Or we can actually keep it just conceptual and still keep to the stats. So we might actually be able to plot the intercepts, coefficients, R's and P values, but we can still calculate them. So even though we might not be able to plot them, we can still actually calculate them and work out what's going on there and sort of create some sort of model in order to look at those correlations, even though we can't possibly plot it. And you can do that over multiple dimensions. Again, not something particularly going to go into here. So big questions. How do I, this looks great, Simon. I love it. How do I do it? So in Excel, there's a chart element that you can add, and there's literally a button as a chart element that you can click on that says linear trend, and you can basically, it will just plot your trend line on your chart. And you can also display do the display equation and display R squared, and it will show you your coefficient and intercept, and also your R squared will appear up on the chart. You can also use some very, very simple commands in order to plot your R squared, Pearson, your intercept, and your correlation, your coefficients, just in very, very simple commands based on those. Sadly, and I do not know why, it's one of those funky Excel things, there is not a simple way to get to the p-value. There is somewhere you can do it within the analysis toolpack, but I don't know if I've mentioned it before, but I'm not a fan of Excel, so I don't actually know how to do it, but there is a way you can get it through from the from the toolpack. Generally, that will only work on a simple 2-variable regression. There are ways of doing multiple variable regressions in Excel, but it gets really, really quite complicated. I think you have to put in the analysis toolpack and yeah, do some sort of wizardy thingy. We can have a look at how to do that at some point. Or we can use my friend R, where basically we can just select a model. We can make a linear model between X and Y and feed in our data, and then say summary model, and it will spit out all the stats and more that we described in like 2 lines of code. And would also, there's like, I can then use my model and make predictions, and there's like a predict function, so I could call my model and say predict what was it 120 in, and it would give me my answer of whatever. So once you've built your model, you can do funky things with it. This does come out with a load more additional statistics I've not gone in and described, but very basically this is our residuals, which is our R values. This tells us what the median of our residuals and how spread out they are. I've just realized that this is not the model for this chart, so that's very naughty of me. But it will also tell me what my intercepts are, and it will also tell me how statistically significant my widgets are by giving them nice little stars. And it also will down here will give me my R squared. But there's some other stuff in there which I'm not going to go into now. So how do we do it? So we did some super simple introduction. Like I say, we can go into sort of next steps and more complicated things another time. There are other things you can do, like say, so you can do multivariate models. So you can feed in lots and lots of dimensions. So you might want to calculate, is there a correlation between the number of GP appointments or sort of the number, I don't know, ED attendances by the number of GP appointments which are going on, the amount of DNAs within this system, and this and this and this, and you can just create massive multivariate models where you can just feed in loads and loads and loads of different sort of variables and work out which ones are correlated and which ones potentially affect the model. You can get into very clever things around sort of, is it a combination of 2 other variables which are affecting your X? So one of them on their own might not affect your X, but actually X sort of Y plus Z will affect X. And again, you can create very quite complex models which can try to look at different variables and look at the correlations on there. Again, I would very much recommend using R for that, because that's kind of the kind of stuff it eats for breakfast. I've not done correlation analysis in Excel. You can do factorial regression. So sometimes instead of just a number, you want to regress on a factor. So quite often we have things like a hospital or a direction, or you know, what it's like north, south, and west. So instead of having something that is a specific numeric, it's in a factor. So you might want to, you know, sometimes you've got a factor and you want to look at whether something is correlated to that. So your factors potentially could be your different systems. So we could look at Devon and Cornwall and all the other different systems and see which ones are correlated, or what factors are correlated to different systems. So instead of just a simple sort of one-to-one relationship, you can look at sort of factors. A little bit more complicated to do, but absolutely possible. And yeah, it uses something called one-hot encoding, which sounds really cool. And it's, yeah, is. You can do logistic regression. So sometimes you want, instead of the number of widgets, you basically got a binary outcome. So you want to know, so has this person been admitted, yes or no, or has this person got sick, or something along those lines. So you've just got a very, very simple yes no type answer. So again, there are ways of saying, well, is this what correlates to this being a yes, and what correlates to this being a no? And you know, one of your absolute classics is obviously using sort of drug use. Did this patient get better by using this drug? Yes or no? You know, did it have an effect? But again, really clever stuff, and uses a lot of the same stuff that we've gone through today, or very similar principles, at least. Obviously, linear regressions give straight line results. Sometimes there are sort of different types of associations between our data. Sometimes we see sort of curves and you know, sort of exponential curves and different distributions, and there are sort of more fancier ways of being able to sort of fit those, which I'm not going to go through there. As we sort of saw, Aaron did his first bit of manual machine learning, which was amazing. And like I say, regression is unbelievably so useful to be able to do those sort of things. And also linear regression is absolutely rubbish at time series. So I keep pumping this out because I don't want to do that. So it's absolutely rubbish at looking at seasonality or changes or how close of a fit data is. So please don't add linear trends to a time series, or if you do, just make sure you are really hot on what your residuals and your R squared looks like. Otherwise, you're just drawing a shonky line on your graph, which is not a good idea. So, final questions. Have you got your head around super simple correlation analysis? Yes or no? Or got a nod. I can only see Aaron, so I'm just picking on you, mate. Sorry, I don't know if everybody else has got their cameras off, but any other yeses? Shout out. Any no's? Or just tell. Is everybody else gone? Fair enough. Do you want to know more? Do you think more widgets need to be sprangled? What was the number from the second slide, which was the answer to this question?
12,402.
Oh, look at you've been waiting for that one, haven't you? Bloody hell, that's massive end points there for you. And finally, any questions at all?
Simon, thank you. That was really useful. Have you got R scripts that you could create into like a library?
I do. And well, I mean, like I said, the main R script was literally on the screen there, like 2 lines long to plot those. So I think within the introduction to R, they show you, or we show you how to add on a linear trend line to a chart. And yeah, happy to pop in there the R scripts to do the very, very simple model and stuff. Ben, you got your hand up.
I do, yes. Just to say that I've still got my IT ticket for getting R installed. I found out yesterday that Tomac got his cube finally installed after 16 months.
Oh, excellent.
So, just wanted to let you know, I don't expect R to be installed tomorrow. No,
I don't know why it's such a problem. I am meeting up with that we're trying to set up an NHS ERA users group, and many of this is what we're going to be pushing, because this is stuff we should be doing and getting our heads around. Any other questions? Maybe about correlation analysis? Stunned. Was that okay? Was that too much? Was it kind of got a head around it? Carly?
It was really helpful, really clear, really easy to understand. Not sure I could make any of the graphs yet, but really good insight into understanding them a lot more, so thanks.
Okay. Rebecca?
Yes, it was really helpful, thank you.
Cool. Leonie?
Yeah, really helpful. I think it was just a bit more sort of layman's terms, which helped.
Yeah, I don't know if you know, but I'm a real idiot, so I just explain things on if I can explain it in its idiot terms, then hopefully other people can. Louise?
Yeah, no, really interesting. A little bit lost on the mathematical equations at the end. And I think putting it into practice with real data and trying to think about it in real terms, would definitely kind of help it sink in for me.
Yeah, I mean the maths is out there. It's kind of good to vaguely understand what it is. I think the most difficult, to be honest, if you can understand that R squared, that's your distance away from your line and all of that. Most of the other metrics kind of piggyback off of that. So if you can kind of get your head around the R squared bit, at least in concept, not necessarily the equation, then you've nailed it, really. To be fair, it's and that's that's the big one about is your line a good fit or not, and that's really important. So yeah, I'm sure if you look around some of our weekly reports and some of the stuff we think, you'll see some of these horrible practices sneaking in, and we need to stamp down on them with my statistical foot. Okie dokie, I've literally got 1 minute remaining. Look at me for super amazing timekeeping. Wow. Any feedback at all? Pop it in the chat. Tell everybody how fabulous it was and how they really missed out on something amazing. I will be, if anybody's got what they would like as sort of next steps or sort of further bits, or if there's anything more specific that people would be interested in, or I'll just rabbit on about something randomly, that's absolutely fine. So do chuck in some feedback. And apart from that, thank you very much. And you've got 6 seconds back. Look at that. Cool. Thank you.
Thank you.
Thanks very much, Simon.
Thanks a lot.
Cheers, Simon.
Thank you.
That was